This conference will now be recorded. This conference will now be recorded.
Okay, well, welcome everybody to GlugNet. We got a good topic tonight, taking a gamble with functional domain modeling. Before we get started, just a couple of housekeeping items. I would like to thank Sam Nasser and NIS Technologies for their support, specifically for the meeting space and recording this meeting. So thank you, Sam, we appreciate that. At the conclusion of the presentation, there will be a SurveyMonkey link sent around. That's an anonymous eval, so we can give Cameron some feedback on his talk. Also, as part of that, if you fill that out, you can enter to win a JetBrains license. Gives you one free product of theirs. Highly recommend it. Okay, and then our speaker tonight, Cameron Presley, is a lead software engineer for SentryOne, a speaker, obviously, a Microsoft MVP, Director of Speaker Relations for Codestock, and co-organizer of Functional Knox.
So, I'm sorry, this is Joe. Can I jump in and announce one thing before we get rolling on the presentation?
Yes, of course.
I want to announce that I just found out yesterday that Uncle Bob Martin, who was one of the originators of the Agile Manifesto and a very great speaker, will be speaking in person at Hillsdale College exactly 2 weeks from today on the 29th. And there are some spots open if you would like to attend in person and see one of his presentations. You would just contact us through the meetup.com website and we will hook you up and see if there's a spot still available, try to get you in. So he's a very good speaker. I've seen him in person before. It's definitely worth the trip. If you're comfortable and you want to have a chance, I would ask you to let us know.
What college?
Hillsdale College in Hillsdale, Michigan.
Oh.
So it would be an on-campus presentation. As far as I know. If that changes, we'll post something on the website, but that's my understanding. So anyway, it's a great opportunity. He speaks all over the country, and we're lucky enough to have one, within a driving range of the Lansing area. So just wanted to bring that forward. Thanks, Steve. Sorry for the interruption.
Oh, no worries. Great announcement, Joe. All right, well, that's all the introduction I have. So Cameron, take it away.
All right. Thanks, Steve. Appreciate that. So good evening, everyone. As mentioned, my name is Cameron Presley, and we're just going to dive right into it and talk about functional domain modeling. So I asked the question at the beginning about how many in the audience has actually had any experience with domain modeling or with functional programming, and it seemed to be a little bit light. So we will kind of take it from more of an introductory level, and I highly advise you to ask questions in the chat as this presentation is rolling. I'm going to pause at certain points in the presentation and ask Steve to help mediate some of those questions for me to kind of help me out a little bit. So first and foremost, what I would like to go ahead and mention is that there's no need to take notes for this presentation. Everything you're going to see tonight is already live. So any code samples, slide deck, resources I mentioned, the whole nine is already live. You can find that information by either scanning this QR code or by going to my blog at blog.softwarementor.com/presentations. I will also make sure to share all this information with the organizers after the presentation so that can get distributed appropriately. So no need to frantically take notes on this stuff. As mentioned before, I am a lead software engineer for a company called SentryOne. For those of you who work in the Microsoft tech stack, if you're familiar with this little thing called SQL Server, and you've ever asked yourself, why is my query so slow? Why is this SQL Server instance so slow? Or why is it not doing what I'm expecting it's doing? Or you're just kind of curious about how your data assets are actually, operating and behaving, and you want some better insights on monitoring it, we probably have something to help you out. If you're interested in learning more about any of these things, let me know. For those of you who actually sling SQL for your day job, check out Plan Explorer. It's probably one of my favorite tools that we've got, and I did some of the initial development on it, which is pretty cool as well. So that's enough about me. Let's cover what we're going to talk about this evening. So we're going to first actually do an introduction of Blackjack. So a little bit of the rules of the game, what exactly we're going to be modeling and what we're not going to be modeling. Blackjack's one of those games where you can make it as complex as you would like, and if we make it too complex, we'll be here all evening talking about it instead of actually writing any code. Once we've kind of went over the rules of Blackjack, we'll actually break down the domain. And I'll show you a couple of tips and tricks I found to be really helpful to identify the domain models in general when problem solving, but in particular for Blackjack. Once we found these different domain models, we'll go ahead and implement them. And the way we'll implement these models is with functional programming concepts in mind. Now, all the code in this evening's presentation is in F#, which don't let that throw you off any. If you've ever done any TypeScript, it's going to look very similar to you. And if not, I'll call out the syntax changes as we kind of run into them. Once we've identified the domain, we've modeled it, we'll actually take a look at how would we model common workflows in the game. For example, drawing a card into your hand or scoring a hand. An entire working version of Blackjack is actually already live on my GitHub, which is one of those links I'll share after the presentation. So with that in mind, let's go ahead and get into it. Let's take a look at what at the problem description here. So at a really high level, Blackjack, the way we're going to model Blackjack, or at least the rules, is that we're going to play with a standard deck of cards. So 4 suits, 13 cards in each suit, 13 ranks in this case. And the objective of Blackjack is that you're trying to get the closest to 21 points without going over. And usually how a game is played out is that you've got one or more players, each of which is playing against the dealer. So it's a player against a dealer, not players against players. So with this kind of overview in mind, how the game's really set up is each player is dealt 2 cards face up, and this forms their hand, right? The dealer is dealt 2 cards, but only one of them is face up, and that is their hand. So there's a little bit of hidden knowledge here of what the dealer actually has. Once the cards have been dealt out, though, starting with a player, that player can take an action. And once every player has taken their turn, the dealer will take their turn. And after the dealer completes their turn, each player will compare their hand with the dealer, and then depending on who has most points or some other conditions will determine who the winner is. So far, not so bad, I don't think. When it is a player's turn, they have a couple of actions they can take though. So an action could be one of the following. So they can decide to stand, which means that they do not want to draw any more cards. They are done. That's the hand they want to stay with. Or they could hit, and by hitting, they draw a card. However, by hitting, their hand may go over the score of 21, and if that happens, they will bust. And unfortunately, their turn will end, and they'll leave the round because they've been eliminated because they went over. Okay. Once you have a hand, you can score it by following these rules here, where an ace can be worth either 1 or 11 points, face cards are worth 10 points apiece, and then number cards are worth that many. There's another special rule in scoring where if a player or a dealer is dealt a hand worth 21 points, so usually an ace and some 10-point card, they have a blackjack winning automatically. Oh my goodness, that's a lot of rules I just kind of pushed in your face very quickly. And if you're like me, you're like, oh my goodness, that's a lot. I might want to take some Tylenol, right? And take a minute here. But at a really high level, that's kind of the game. So with that in mind, let's start breaking this down. Let's examine a little bit closer at the problem. So when I think about breaking down a problem or a domain, a common technique one can use is finding the nouns. So what we're going to do is we're actually going to go through this problem description again, a little bit quicker though, identify the nouns, and then those nouns will kind of help us start shaping out what this problem and what our solution is going to look like. There'll be plenty of times where I'm going to ask you all, what do you think the nouns are? And we'll see what you all think. And if you don't tell me what the nouns are, I'll just start like calling on people, taking guesses, and this can get super awkward really quickly. So you might want to help me out a little bit here. I will also say there's not like just one answer. This is just my interpretation, right? So if we recall, our first description was this, right? We've got a game played with a standard deck of cards. The objective is to get closest 21 points without going over, and it involves one or more players playing against the dealer. So does anyone either want to shout it out or put in the chat what they think a noun in this description could be?
Card.
Okay, yeah, someone said card. That sounds like a great option. Any other ones that come to mind?
The game.
Oh, whoever said game, excellent. Yeah. So we've got a game, we've got card. How about deck? Deck sounds like one of those nouns, right? Okay. What are some other ones that may be standing out here? Something that sounds like related to the problem.
Point.
Player.
Points, players, those are great options. Those are all excellent. I think you all actually got everyone I had. I think the only one, that was missed was dealer, right? Because dealer is kind of a special concept as well. So we'll take these nouns and we'll actually just make this little graph. So we have these little circles and they have the name of, and they have that noun in each circle. Because right now what we're doing is we're kind of trying to identify all these concepts. And once we have these concepts identified, we can start modeling them. So let's keep looking at this problem description, see what else comes up. So the next part is we had each player's dealt 2 cards face up to form their hand, and then the dealers also dealt 2 cards to form their hand. Are there any nouns here that we haven't already covered?
Hand.
Yeah, hand. Hand's a great one. In fact, I think it's the only one we had here. So, all right, cool. So now we add hand into the giant list of concepts that we'll need to model. So let's keep taking a look. So here we were talking about, on the turn, a player can take an action. Once all the players have taken their turns, the dealer can take their turn. And after the dealer takes their turn, players will compare their hands with the dealer. Are there any nouns here that we haven't identified yet? Because we've already gotten player and dealer. Those have already been handled. So are there any other ones?
Turn be one.
Oh, turn's a good one. Hold on to that one. So let's hold on to that one for a minute. But turn's definitely a good option there to be thinking about. Are there any others? Okay.
Action.
Yeah, bingo. Action. Yeah. See, as we're describing through this, right? If we're going to be asking questions too, like, so when someone says an action, what is that? What exactly do they mean, right? Like when we say hand, what is that concept? And by asking these questions on the domain, we're going to have some pretty cool ideas on how to model this more effectively. So, all right, cool. We add action to our list of concepts here. We could have also added turn. You'll see a little bit later on why I didn't do that, but we totally could have here. So we kind of go here to the next slide, right? And so players can either do one of 2 things, right? They can hit or stand or stay is the other way of describing that. And if their hand goes over 21, they bust, ending their turn, leaving the round. Are there any nouns, anything here that's kind of standing out? Especially from like a terminology perspective.
Round.
Yeah, so there's definitely a concept of a round, right? There's a couple other ones here too, right? Like stand and hit, like what are those things? And this idea of a bust. And so what we find is that this hit, stand, and bust, they all rely to this concept known as like a status of some sort, right? Like there's like some type of player status or dealer status, whether they busted or stayed or something. So pretty cool. So this is what we have so far is we've got all these concepts, we've identified them, but we don't know how they relate to one another yet, but we know they do, right? We know they're going to relate to each other at some point. So now that we've got this, we can actually build up a dependency chart. So we can figure out how these things relate to one another. And we can do that by using this has a methodology, right? If you're coming from object-oriented, you're probably used to the is a technique, like square is a shape, circle is a shape. What I found to be really helpful when determining dependencies on what depends on what, I find has a being super helpful. So for example, someone mentioned game earlier. So as we start building these things out, we know that a game has a deck, has to have a dealer, and also has players, right? Because you have one or more players, right? And as we dig deeper, we know that a deck has one or more cards. Okay. And then, so now that we've got like deck and cards kind of related, we know a dealer has a hand. We know that player has a hand. And we know hands have one or more cards. Well, and as we keep digging, right, we're digging through this, we find out like, oh yeah, well, card has this concept as a rank in a suit, and you go, oh crap, what's that all about? And as we keep digging through this stuff, we'll add more concepts, right? So in this case, rank and suit were some new nouns that we didn't think were a thing, so we add them to the giant list. But what we can do then is after we've got some of the stuff like identified, we can put some arrows to it. So now we have kind of this dependency tree of, okay, well, if you got a game, it's got these things, and if you've got a player, it has to have these things, and so on and so forth, which is pretty neat, right? Because it kind of lets us know all the intricacies. And what's also kind of interesting as well is that the status points in action, they seem to be their own thing. They don't seem to be related to any of the other stuff yet, which interesting, kind of cool. So let's take a little bit of a deeper look into this. So this tells us from a top down, but if we wanted to implement all of these things, we can rotate it. We can rotate this chart, flip it upside down, and this kind of gives us an idea of how we need to implement these things, right? Because we can't implement a card until we figure out how to model rank and suit, right? We can't model a deck until we can model a card. So this is kind of a cool way for us to break down a bigger problem into more consumable parts. Because could you imagine trying to model a game and then trying to have to model everything else as part of it? Probably a bit rough. How are we doing so far? Are there any questions in the chat? Is this kind of making sense here a little bit about how we read through the problem description, identified some nouns, and then came up with the relationships between them?
I don't see any questions so far.
Wonderful. Okay. Well, so we've identified all this stuff. Let's get to modeling. Let's actually get to typing up some of the stuff. So let's start with a rank, right? And so what will happen is throughout the next section of the presentation, we'll update these notes, color code them essentially to say whether we've implemented them yet or not. So with rank, let's start there. So rank's pretty cool. So a rank is the technical term for like one of these 13 possible values a card could have. And this is where it can be an ace or a 2 or a 3 or a whatever. So take a guess, right? Just how would you model something like this? Anybody want to just say it out loud, like a way you would model it?
Enumeration.
All right, cool. So I see an enumeration, I see a set. Okay, so let's take a look how we would do this in a functional data. Whoever said enumeration, like excellent, because so in functional programming, we have this concept of a type called a sum type. And what a sum type allows us to do, it is a type that says you can be one of a finite number of things. So when you first look at sum types, a natural assumption is that it's an enumeration or an enum of sort. But in reality, each of those choices is its own thing. It's its own type. It has its own constructor, is what you'll typically hear it called as. But what's nice about this is that if you have a data type that you're wanting to model that can only be one of a possible thing, like A or B or C, some types do a great job of modeling that. In fact, let's take a look how we would model the rank type. Here it is. So this is some F#, but a good way to read this is that we've introduced a new type called rank, and then the different constructors it has is the ace constructor takes in no parameters, but it's called ace, or there's the 2 constructor takes in no parameters, so on and so forth. And by defining rank like this, I can't come up with another one. Like if I try to define a value called of a type rank and said, well, that value is like banana, I would actually get a compilation error. It literally wouldn't compile because banana does not belong as one of these possible constructors for rank, which is pretty cool. The reason why I prefer some types to modeling this type of stuff over enumeration is that if you've been in .NET for any period of time, you know you can kind of get around enumerations by like typecasting an integer, right? You could take the number 100, typecast it as like I think the month enum, and it would actually compile. It would work until you try to do something with it. With some types that literally wouldn't compile, wouldn't even work. So that's kind of nice. You're preventing developers from making mistakes essentially. So we've looked a little bit at some type. We've been able to model a rank. Let's take a look at the next thing. Let's take a look at suit, right? Because we've got rank updated now. Let's look at suit. So suit, very similar to rank in the fact that it represents one of 4 possible values. And we know that a suit can either be a heart, club, spades, or diamonds. So given what we've seen so far, how would we model this? Anybody want to take a guess?
Sum type.
Yeah, use a sum type. And yeah, and the definition of it's pretty straightforward as well, right? We say we have this new type called suit, and it can either be hearts or clubs or spades or diamonds. It can't be anything else. All right, cool. So we've got rank and suit defined. We can now work on card. So card represents the combination of any rank and suit, right? So it can be, if you've got 13 ranks times 4 suits, that's 15 possibilities. So what are some ways that we can model combinations of types? This is something new, right? Because you could technically model this as a sum type, but that means you would have a sum type of 52 options, right? And then it would be stuff like ace of spades, 2 of spades. Probably not a great way to model that. So how do we model combinations? Well, if you're from OO, you're probably thinking things like a class, possibly a struct, maybe even a tuple. Well, in functional languages, we'll typically use something known as a product type. And so a product type is literally what it sounds like. It's the combination of other types, and it's the literal mathematical product of the possible values for all the types it combines. And so if we need all the possible values of rank and all the possible values of suit to model a card, this is what it would look like. So we define a new type called card. It's got 2 properties. I think the technical term for this is labels, but it's got 2 of them, one called rank, one called suit. The one called rank is of type rank, the one called suit's of type suit. And by modeling card this way, it will immediately be able to represent any combination of rank and suit. Pretty neat. And once again, based on the way we defined rank and suit, you can't really give me like a card that's not valid in a deck of playing cards. Like you can't make a 4 of bananas out of this, right? Because banana is not a valid suit. Kind of making sense so far, a little bit here.
So if you were playing a different game that say had jokers involved with it, would that joker fall under suit or rank?
Ooh, now that's a really fun question. So jokers do not have a rank or a suit, correct?
Mm-hmm.
So what we would do is sounds like card would be an or type then, right? It's either a card of rank and suit, or it'd be a joker. Joker would be its own data constructor in that set.
I see. Okay.
Yeah, great question. Ooh, very great question in the chat. What about cards with conditional values to ace? Hold on to that one, Rich, because we actually will cover how we deal with that. Right. So, and the reason why I actually want to call out that question too is when we're doing data modeling, right, we're trying to model the data as the way it's supposed to be interacted with, right? So Rich has already identified like, well, we know that when we get to dealing with aces, that's going to get a little bit weird. Yeah, you're probably right. It is going to get a little bit weird. And we'll tackle that problem when we get there. But I will say that you've already seen a hint of how to deal with that already so far in the presentation. So really, really good question there, Rich. So, okay, we've got rank, suit, and card. And so because we've gotten those 3 concepts modeled, now we can model like deck, we can model hand, we can keep going forward. So let's take a look at deck. So deck represents the cards to be used in the game, right? That's kind of what its goal in Blackjack is. And throughout the course of the game, players and dealer, sorry, I have typo there, will be drawing from this deck during the game. So it's going to have to be some structure, something that can change size throughout the course of the game. So how do we model this type of thing? Well, if you're thinking back to your C#, you're probably thinking like, well, list makes sense. Maybe those who's got a little bit more of a data structure, you're thinking a stack might work. Well, we can do something like that. So we're going to create something known as a type alias. And what we're going to do is say that, well, the deck type is really just a card list. It's really what all that is. And so what this will do for us is that it says any code that can work on a card list will also work on a deck, which is kind of nifty about that way. The list type is an actual type in F#. It's more of a linked list. So it's not like a list in C#. It's more of a linked list. But you can still do things, right? You can for each over it, you can map over it, you can still do all those things on it. Just realize it's more of a linked list and the fact that it's got a head element and then the tail, the rest of it. But yeah, by doing this a little bit of a type alias, we can say, hey, if you say that this is a deck, it's got to be a list of cards. So if we've got a deck modeled out, we can take a look at hand now, right? And so hand, it represents one or more cards that a player or dealer has, right? Something that they've got. And it's also going to be kind of changing throughout the course of the game, right? Because at the beginning they have 0, but then they get their hand, which is 2, but then they could hit, so that means they can draw more. So it's got a little bit of that similar vibe as a deck. So we can do the same thing, leverage a type alias here, and say, all right, well, a hand is also a card list. But now there's a small problem. Well, we've said that hand is a card list and the deck is a card list. And the reason why that could be problematic is because they're the same type alias, that means they're interchangeable, right? Because we just said if hand is a card list and deck is a card list, that means I could pass in a hand into components that are expecting a deck and vice versa. Don't you think it'd be a bit weird if you could, instead of drawing a card from the deck, you could draw a card from your, like, another player's hand? You think that'd be kosher? No, probably not, right? So what can we do, right? Because we've now identified that, hey, wait a minute. Yes, a hand is a list of cards, and yes, deck is a list of cards, but they should be treated differently. Okay, what we can do is use that sum type trick again. So what essentially we're doing is we're going to redefine deck, and we are saying, hey, if you're a type of deck, you actually have a constructor now. You're actually saying, and this is the trick right here. So by adding this deck of card lists, we're now saying that if you create a deck, you have to pass in a card list, and we're essentially going to tag it and say that's a deck. The minute that we do this, deck is no longer a card list. Trust me, I know this is a bit abstract. Let me show you what we really just did in like a C# analogy. So here's some C# code, right? We've got a public class that inherited from a list of card. Nothing crazy. And now we've said hand equals a new list of card, and we've said deck equals a new deck. So let's say I write this function now that says, given a deck, I'll give you back the length of the deck. Right, so we pass in a deck, we just call count on it, pretty much what it does. So if we call get length on deck, that'll actually compile the work, we'll get the count. But when we try to call it on hand, we actually get a compilation error. And what we'll be told is like, hey, wait a minute, you told me that get length works on the type of deck, but what you're passing me in is a list of cards. Those aren't the same thing, so I can't work. Even though deck actually inherited from list of card, because we said that this only works on deck now, you can't pass in a hand. See how we're preventing, by being a little bit smarter with our data modeling, we can prevent developers from making mistakes by passing in decks into things that, or sorry, by preventing developers from passing in a hand into things that should only work with a deck. So I'm going to pause here and see if there's any questions or anything else I need to elaborate on, because this is kind of one of the cooler concepts. Cool. I'm not seeing anything in the chat. No one's coming off mute. So final shot. All right. Okay. So we've now got this concept of a player, right? So we've got deck and hand wrangled, so we can go to player, so we'll take a look. So player represents someone playing the game. And a player really has two things, right? They're going to have a hand, and then they're going to have something known as an ID. And honestly, you could probably get away with not having an ID, but the reason why I keep it is so that you can keep track of who's player one versus player two. But there. Oh, I'm sorry, I've totally missed the question. So Rich Hamilton asks, so you're saying that deck is defined recursively? No, that's not what I'm saying. Not at all. So that's a good question though. What I'm saying is that if hand represents any card list, deck now represents only card lists that have been declared as a deck. Like I actually added, like I've actually passed it into another type. And so if we, I'm gonna pop the stack a little bit here real quick. So if we go back to the C# example, this is closer to what we just did, right? Like we have a list of card and I've said, hey deck, you're everything that a list of card is. But now when I write functions that say you work on a deck, it has to work on the deck type. It can't work on just any list of card. So there's no recursive definition. There's nothing like that happening here. Does that kind of help?
So can you go back to the explanation you gave? We're only using of. That's the only difference.
Yeah. So the minute we say deck of, we are actually forcing a constructor to happen there. Also, my screen just froze on me, so I'm not sure what you're seeing. So I'll get that resolved in a second.
C# still.
Okay, perfect. So I'll get that resolved in a minute. But yeah, when we did deck of, we're essentially saying, okay, it's not any card list. To create this deck, you actually have to say deck parenthesis some list of cards. And the minute we do that, we've now elevated. We've now said, hey, this list of cards is specifically a deck.
Okay.
That is the difference. So I'm going to go on mute for 2 seconds while I fix my screen freezing issue, hopefully, and we'll get back on track. Hey, can everyone hear me okay still, or no, not so much?
Yeah, I can hear you.
Cool. It looks like you lost my presentation though. My apologies. Give me 2 seconds. And for some, wow, GoToMeeting just totally just decided to turn off everything for me. That's cool.
We can hear you though.
So sorry about that. Oh, good. So let's get back on track, but don't jink. Oh, super bizarre. All right. So let's get us back on track. So if everything's working correctly, again, you should be seeing some C# code of some sort.
Yes.
Hopefully. Perfect. All right. So sorry about that. I didn't mean to hang you all up. Let's take a look here. Good. All right, sweet. All right, so I'm going to try to get us back onto talking about player, right? So player has a hand. They also have an ID. They don't technically have to have an ID, but I would like to put one in so I can differentiate between a player one and player two, because just in the off chance that we're playing a game with multiple decks and somebody happens to, and two people happen to have the exact same hand, they are technically different players, hence the ID. So how do we model something that has a hand and an ID? Well, we use that record type, that product type. We essentially say, well, a player is anything that's got some integer for an ID and then some hand of type hand. And the kind of nice thing about this too, as we're defining this, is that there's a little bit of functional jargon, but you could probably actually hand this over to like someone who's a domain expert in Blackjack, and they'd be like, yeah, this is kind of making sense so far. There's not like, you're not having to explain like what a class is and what's a public thing. And you'll see a little bit more of that in a minute. So cool. So we've done player. Let's go to dealer. So dealer is really easy because this represents the person that every player is competing against, and they only have a hand. So we're going to model that as like a simple record type, and it just has a hand. Not much more past that. You don't have multiple dealers, at least not in the way we're modeling it yet. Though knowing product owners, they'll tell us, like, well, of course you have multiple dealers. Why didn't you think about that? But for right now, we'll keep it with one. So cool. So we've been making pretty good progress on this so far. So let's take a look at how we do a game. So we've got a game. It's what's being played, and it consists of a deck, a dealer, and one or more players. So does anybody want to take a guess on how we would model this? Just another record type, just another product type. This idea that a game is a combination of all, some players, a dealer, and a deck. So not too bad, I don't think. Not too bad. Okay. So let's keep working through. So we've got 3 more components we need to model. This idea of a status, this idea of points, and this idea of action. So status, this is something that a player or dealer would have throughout the game, but we're not really sure like what everything is about so far. But after talking to the product owner, we realized like, hey, there's a couple of possible values here. You could either have a blackjack status, you could have a busted status, or you could have a state of status, like you stayed with some value. So the way we can model that is using the sum type. And somebody was asking earlier about that of keyword. Here's a great example of that in play. So the status type can be one of 3 shapes. It could be an integer that was constructed using stayed. It could be an integer that was constructed using busted, or it's just a constructor of no parameters called blackjack. And the reason why we decided to model it this way is that for blackjack, the reason why blackjack doesn't have an integer is because if you have a blackjack, it's 21. Oh, excellent. So a couple questions in the chat. So game didn't game in the noun object model. I'm not sure what that one's about, but I'll skip over that for a minute. Rich Hamilton asks, what is the status of a player that continues to take hits? So remember that their status isn't really like defined until they've done one of these 3 things, right? So if they're blackjack, there's nothing else for them to do, right? They just keep going, like they don't even take a turn, they're done. But until they either bust or they stay, they just keep drawing cards. So that's why I didn't force the status as part of the player, because you'll really just develop the status at one point. Like pretty much when they're taking their turn, after that, you never really have to touch it again. So good questions there. Yep, and we just talked about how to construct this stuff. So just got ahead of myself a little bit there. So such a player has no status, at least the way we've defined it so far. That may change throughout the presentation. But yeah, so right now a player does not instinctively have a status at the very beginning because you don't know what their status is, not always. So let's take a look at points. So points represents how much a card is worth. And someone asked earlier, and I believe it was Rich, was like, well, how do you deal with aces? Because aces are weird. Yeah, aces are a little bit weird, aren't they? So an ace can be worth 1 or 11 points, face cards worth 10, and then number cards worth that many. So we can model this in not too bad of a fashion, but the trick here is realizing the ace, right? 1 or 11. So what we can do is we can actually model it as a sum type here and essentially say like, well, points can have one of 2 shapes. And the reason why I chose hard and soft is that that's actually the domain terminology. Like if someone says they have a soft 17, that actually means they have an ace and a 6. That's usually what that means. But so what this type tells us is that, well, if we need to construct the hard, or if we have an integer, we would construct it using the hard label. So so if it's like, let's say it's a king, then its points value would be a hard of 10 because it can only represent one integer. But for the soft type, we actually need a tuple of int and int. So for the ace, we would say, look, that's a soft 1,11. And so that's how we can actually model that. And this is one of the, actually one of the most powerful things I really enjoy about functional domain modeling is that I can take disparate constructors and glue them together to make a type that is uniform. It would actually been pretty tough to try to pull this off in a more OO language, not unless we started doing like a lot more constructors and a lot more like trying to define interfaces and such. It gets kind of sticky very quickly. But with this kind of falls through pretty naturally. And you'll see how when we start like doing some of the workflow implementation. The other thing I'll mention here real quick too is that besides looking at sum types and product types and type aliases, we've not had to really bust out a whole lot of like design patterns or anything crazy like that. We've been kind of following our nose here, which has been nice. Question from Rich in the chat. The asterisk is the separator for tuple elements? Absolutely. So when you're defining the tuple type, it will be denoted with a star. When you're wanting to consume it in code, it'll be with the comma. So very, very similar to how you consume tuples in C#. All right, last but not least, actions. So we talked about this, right? Represents what a player can do during the game. I say player, but it's really the player and the dealer. Well, ish. And in this game, it can be hit or stay. But in other flavors of Blackjack, you can do things like doubling down, splitting, all that other stuff. But since an action can only be one of two things, hit or stay, we can actually model this pretty well using yet another sum type, right? So we have a type of action, and it's literally either hit or stay. So if you haven't gotten sick and tired of me saying sum types yet, don't worry, there's more. There may be something to it. Oh goodness, we just defined all this stuff. That's pretty cool. You know what the scary part is? Here's all that code. Here's technically all the domain modeling we had to do for Blackjack. And it's like 15 lines of code. This would have been really hard to have pulled off in an OO language to be this succinct. Also, there's a couple of syntax things you would have had to explain to like a product owner, like what the heck does the star do? But in reality, if you just essentially explain like, well, the pipe means or, and if you see the curly braces, that means like for card, that means and, like it's a rank and suit, you can almost read this off like English, and your product owner will be like, yeah, that kind of makes sense, which I also find really powerful. So I'm going to take a pause right here to see if there's any questions about domain modeling or any of these things so far, because the next section is where we actually start playing the game a little bit, doing some of these workflow modeling type tasks. So I'm going to pause here and see if anyone wants to come off mute or throw their questions in the chat, because Rich has been doing an awesome job lighting it up in chat. Okay. Given about 10 seconds. If you haven't found your mute button yet, probably not going to be able to happen quick enough. So let's take a look at doing some common workflows. So of actually playing the game. So let's go with shuffling. Like, how do we actually create a deck of cards? Because we've defined the type, but how do we actually do it? So here's a whole bunch of F# code, and it's terrifying, but let's break it down. So at a really high level, we're going to create a function called create. It takes in no parameters except for this open close parenthesis thing that you'll know as unit. And it's essentially a placeholder. So no parameters is the closest thing I can explain it to you as right now. And so we've got this function called create. And what it's going to do is it's going to take in no inputs, and it's going to give you back a deck of cards. So the first step we're going to do is we're going to define a list of all possible ranks. So that's your ace through king, and all suits, hearts through diamonds. And then we're going to write this little helper function called tuple to card. And what this will do is if you give it a tuple where the first element is a rank and the second element is a suit, And Rich, this is going back to where we were talking about earlier, where the comma helps is how you actually break down a tuple. Then we'll say, okay, we're going to give you back a card where the rank field is set to R and the suit field is set to S. So now that we've got this in play, we can actually build up creating the deck in the next section like so. So in F#, the list module is kind of where you have all the things that work on lists. So if you're used to link, this is where you would find things like select, where, aggregate, those types of things. However, in the F# module, we have this really cool function called all pairs, and it's exactly what it sounds like. It will create all possible combinations of two lists. So in this case, rank and suits, and it'll actually create them as a tuple. So once we call all pairs, we now have a list of tuples. Well, for each of those tuples, we're going to convert them using the map function and tuple to card into a card object or into a card type. So now we have a list of cards. Now, for those of you playing along at home, you realize, well, a list of cards isn't just a deck, right? There's one more step we got to do. And that's what this third line does. This third line actually shoves it and constructs it as a deck. So at this point, we really truly do have a deck to work with. One thing you may have noticed though is this interesting pipe arrow operator. You'll typically hear it referred to as a pipe forward operator, which means take the thing on the left and shove it at the end of to the thing on the right. The reason why this is really cool is that in functional programming, this idea of developing pipelines and workflows is really common. So it's very common to see a little bit of data orchestration happen at the beginning of a method, like we did here, and then pipeline everything to spit back the result. So I know this is a ton of F# code, so I'm going to take a pause here to see if there's any questions about either the syntax or the flowing of things so far.
There's something I'm wondering. Is create the entire code, or is it just okay?
So let's chat about that. That's a really good question, and I believe that was Daniel, right?
Yes.
Yeah. So in F#, it is white space delimited will kind of tell you so indentation tells you like what belongs to what. So very similar to Python. So the create function, after the equal sign, everything that's below it and tabbed over one, like literally tabbed over, belongs to the create function. And so the other thing that can throw people off when dealing with a functional language is that there's not really an explicit return statement. So that's probably what's thrown maybe a few people off too, is like you're wanting to see a return somewhere here. No, that's actually not how it works. So in most functional languages, whatever the last expression that was computed is the return. So since I just did list all pairs, then mapped it and then shoved it into the deck type, since this was the last thing in the function, that's actually the return. It's implicit that way. Does that kind of help?
Yes.
Yeah, cool. Rich asks in the chat, the pipe forward operator would be analogous to a redirect in an operating system command line. Yeah, kind of. That's one way to think about it, right? You're taking the output of the left and shoving it to the right. Yeah, that's not a bad analogy at all. Just that, in this case, you're not shoving it into, you're not really redirecting it to a file or anything like that. But yeah, that's not a bad analogy at all, Rich. Great questions. Are there any more? Okay. So at this point, we've defined a create. So this will give us a deck, but for those keeping track, you'll realize that, wow, this deck is kind of ordered, right? Because it'll be the ace of hearts, followed by the 2 of hearts, followed by the 3 of hearts, followed by the 4 of hearts. And if I know the deck is always going to be that way, I know exactly when I should be betting and whatnot, right? We should probably figure out a way to shuffle. So let's create a shuffle function. So you're probably already looking at this going, what in the heck is that? So this sorter, So the way to read this shuffle function is if you pass in some function that says given a card, return back an integer, the shuffle function will then give you back a deck. And we can kind of see right here how that's going to work is that we call that create function, and then we're going to sort by that sorter. So it's going to essentially, for every card in the deck, call the sorter on it, and then it'll sort by whatever that integer is. So a really common way to define a sorter function is I don't care what the card you passed in is, I'm just going to give you some random integer between like 1 and 100. That's one possible way of implementing a sorter. But the idea here is not for you to get really hung up in the F# syntax, but really think more about this pipelining thing, right? Like, okay, well, we just went from, we had a function called create, so now we've got a deck, but now we got to shuffle it. Okay, well, how do we shuffle it? Well, we need a way to essentially sort cards. And now that we've got a way to create a deck and a way to sort a deck, we can then pipeline that. Yeah, create another workflow, another pipeline to work with on this, which is pretty cool. So we're taking smaller functions, composing them to make bigger functions. It's kind of the idea here. So cool. Oh. Let's talk about scoring, right? There's been a couple of questions about like how would you score hands and score certain concepts. Let's take a look at that. So I'm just going to put it out to the audience. If you had a hand, so that means you've got a couple of cards, how would you high level score it?
Sum the values.
Yeah, so exactly. You would have to figure out how much each card's worth, right? And then sum them up. And Dan, I believe that was you again who said that. Yeah, and you kind of like matter of factly said like, yeah, you just add them up, right? And so cool, let's do that. So scoring rules, right? Aces are worth 1 or 11, face cards are worth 10, and then number cards worth that many points. So we've got to define a function that says, given a card, let's figure out how many points it's worth, and then we need to figure out a way to add points together. So let's take a look at figuring out how much a card's worth. No, we can write this function. So recall that points, that type had one of two shapes to it. It could either be an integer called hard, or it could be a tuple of integers and we refer to it as soft. So then we write a function called card to point, and we're going to call the input C, and C is going to be a card. Once we've passed in that C, we can match on its rank. So this concept's known as pattern matching, and C# has been getting a lot better at it in the last couple of releases, but man, functional languages is still pretty solid. So I can match on that rank and say, well, if it's an ace, I'm going to give you back this soft value of 1, 11. And if it's like a 5, I'll give you back a hard value of 5. And if it's a 10, jack, queen, or king, I'll give you back a hard value of 10. One of the cool things about pattern matching and functional languages is that, let's say I forgot to define what to do if the card was a king. Let's say I just forgot that case. The F# compiler will warn me, hey, by the way, you totally forgot about this thing. Like you totally forgot to handle this. And if you turn on one of the settings in the compiler, you can actually make that a build error instead of a build warning. But that's kind of nice that the pattern matching is actually pretty advanced on this stuff, that it will tell you like, hey, by the way, you forgot this case. And in fact, let's take a look at a more complex example of pattern matching. So we've got a way to go from card to point, but now we've got to figure out a way to add points. And this is a bit tricky because these just aren't integers, right? There's tuples involved. There's this hard and soft thing. We've got to define the rules, so let's do that. So we're going to define a function called add. And it's going to take in 2 parameters. And I'm going to call the first one A, and I'm going to call the second one B, because honestly, the names do not matter. And so the signature of add is going to be, if you give me points and points, I'm going to return you points. So the first thing we're going to do is we're going to pattern match on them. And this, to me, is the cool part. Well, if both points you've given me are hard, that means I've essentially got like a hard 10 and a hard 7. Then I know the value I need to pass back is like this hard 17, right? Just pass you back the sum of those two. Well, if one of the points is a hard value and the other points is a soft value, then I know the way to combine them follows this formula. So in this case, let's say we had like a 7 and an ace, then we know we need to return back a soft value of 8 and 18. And here's the fun part. If I had forgotten to cover the soft and soft case, the F-sharp compiler would have picked up and said, hey, by the way, you totally forgot to cover this. You probably should do something about that. But in the case of soft and soft, that means I've essentially gotten 2 aces. So you can work it out on paper, but what you'll realize is that in that instance, you can pretty much throw out one of the high values and then do the math and you'll get pretty much the right numbers you needed. So soft x plus e and y plus e in this case. So we've gotten a way to go from card points. We've got a way to add 2 points together. So here's how we can calculate a hand. So the signature is you give us a card list, we'll go to points. So we take a hand. Remember, a hand is a card list. So for every card, we'll convert it to points based on our card to point function we wrote earlier. And then once we've got a list, of points, we'll reduce that list down to a single value using the fold function. So very similar to aggregate from link. And then say, all right, well, I want you to reduce these things by using the add function. And I want the first value for you to use to be a hard value of 0. That's pretty neat, right? And Dan, I believe everyone said it, right? You're like, well, yeah, figure out what each card's worth and add them up. Well, crap, that's what we just did. Not too bad. So I'm going to take a pause here and see if there's any questions in the chat or from the audience.
Could you go back to the add thing?
Sure. Yeah. Okay, while people are stewing on this, I'll check out the chat. So, oh goodness, I feel like I've missed this by like 20 years ago. Rich asks, would a card being drawn from the deck be the index value of the set that comprises the deck? We're actually about to talk about how drawing from the deck works. So if you can wait about 2 more minutes, you'll see how that goes. The order of A and B does not matter. Oh, that's a great question. So asked, I'm going to try the name here, Yusuke. The order of A and B does not matter. It does not matter in this case because addition is commutative, right? It doesn't matter if in either of these operations, right? If both the cards are hard values, then addition works that way. And then for that middle case, I'll back it up a little bit. You'll see that they're tagged exactly the same, right? So hard of X, soft Y is E, soft Y is E, because the order doesn't matter there because addition's commutative. So that actually helps out in my case. But if order did matter, then I would probably have broken those up into separate cases and then handled it that way. That's a great question. Oh, Rich asked, that's great for 2 cards, but what about hands with more than 2 cards? So if we go back to calculate hand, that fold is the magic, because what fold does, or aggregate if you're from link, it only ever adds 2 values together. Because what fold does is it takes a list of things, an initial value, and a way to combine 2 elements. So if you start with a list, it'll start with an initial value of 0, it'll grab the first item off the list, and then combine them into a new element using the add function. So now it's got a new value. It then grabs another element off the list, throws that element and the previous element, like the new value it just calculated, shoves it in add, gets a new value out, and it'll keep doing this. So that's the beauty of this, is that since I had to define how to add 2 points together, with the power of fold, it doesn't matter if this hand had 1 hand or had 1 card or 100 cards, this would work. Correct. It does not matter if the ace is drawn first. Absolutely. These are all great questions. Are there any more? Okay. So I think Rich has asked this question. I know Rich has asked it at least once. I think someone else has too. Is like, how do we draw a card? So if we think about drawing a card from a deck, right? So we have some deck of D, right? And the signature of drawing is really given a deck, I'll give you back the card that you drew and then the rest of the deck, right? Because in F# and in most functional languages, you want your data types to be immutable, so you can't really mutate a deck that way. So what we'll do is we will try to match on that deck. And since we've unwrapped it by throwing away that deck type, we now have a card list so we can do all the tricks we were doing before. That we can now use all the list things. So what we've done is we've taken that deck, we've now deconstructed it to be the top card of the deck and then literally the rest of it. And if we can do that, then I say, all right, here's your tuple back where the first element is the card that you drew and the second element is the rest of the deck. But you'll notice you may be able to see this or not, I'm not sure, but there's a little orange squiggly around D there. And if we take a look, it'll say, hey, wait a minute, you've got some incomplete pattern matches going on here. You didn't cover the fact that the deck was empty. And then you're like, oh, crap. How do you handle an empty deck? So, because you know in normal gameplay that shouldn't happen, right? Because that means you're playing with like, I don't know, 15 players or something. You're probably not going to do that. But the compiler's telling us like, hey, by the way, you totally didn't handle this. You might want to think about that. So what can we do, right? And the question is, what do we do if the deck is empty? So I'm going to introduce a new type. So in other languages, you have the concept of null, right? And a null can represent the absence of value. The problem with null, though, is that in most OO languages, everything can be null. So you have to do all this like special error handling, all this special stuff to make sure that like, well, if it's null, not chuck a null reference exception, but do other behavior. And so, but the problem with that is that with nulls, you have to be the compiler, right? You have to be smart enough to remember to handle that. The compiler can't really help you out a whole lot. And that's not so great. So we're going to create a new type. We're going to call it maybe. And it's going to allow us to model the fact that a value may or may not exist. By introducing this maybe type, it will actually force the compiler to help us and remind the developer, hey, by the way, you forgot to do this thing. Let's go do that. And it also forces us to actually handle our error conditions, which I don't know about you, but I'll sometimes forget about that. So anything that forces me to do the right thing, I'm all for. So here's the type signature for maybe. If you're used to working with generics, you can squint your eyes and say that apostrophe T is really just T. And since you've seen some types a couple of times, you know that this is a signature of either a constructor called none that takes no parameters, but that's what it is, or there's a sum constructor and the value it takes in is that generic, right? Whatever the type is. What's really cool is that most functional languages have this construct already. In F#, it's called option. It may not be immediately obvious, but in C# too, you would actually notice your nullable primitives, right? Like if you do a nullable int, it kind of has some of the same vibe to it as well. It's not quite the same, but it's close enough. So what we can do now is, now that we've got this maybe type, we can come back and actually make the draw function work correctly. Because now we can say, well, if there's nothing in the deck, I'm going to give you back this none value because there's nothing to work with. But if there is a card and the rest of the deck, I'm going to wrap that up in a sum. And by doing that, I've made this function signature a lot more apparent to consumers by calling this function that says, hey, you can pass in the deck in here, but you may or may not actually get back anything. You may, like, because I said option, it's telling you like, you may not get back the card in the rest of the deck. You may just get nothing to work with. And because we've done that type signature, like anybody who calls this function has to deal with none. They have to deal with this idea that by drawing a card, you may not be able to draw anything. So you've seen how we draw one card, but you know what? I hear in Blackjack, most people don't draw one card. I hear you actually draw two cards at the beginning, right? So let's take a look at some really awful code that does that. So Okay, so Rich has asked the question. We'll come back to that one, Rich. So let's draw multiple cards. So we've got this draw multiple function that says, if you give me a deck and a number of cards you want to draw, I'll give you back those cards drawn and the rest of the deck. And I might be able to do that for you. And as you take a look, there's a little bit of recursion, but we essentially say, well, if the number of cards to draw is 0, then I'm going to give you back what I've built up so far. Otherwise, I'm going to pattern match, and if I have nothing to work with, I'm going to return none. Otherwise, sorry, I've thought PowerPoint was catching up with me here, but not so much. So let's try that again. So if we need to draw some more cards, we'll do that. We'll match what we currently drawn so far. If there's nothing, because we've already failed previously, we return nothing. Otherwise, we have cards and we have a deck. So then we'll draw. And if that draw were to fail, we return back none. And if it succeeded, we've got a new card and we've got a deck. So then we recurse. We essentially say, all right, cool. Decrement none by 1. Here's what my hand is so far, and here's the deck. But if you're looking at this, you're like, oh man, that's a lot of code. And this is not exactly super easy to understand. Mostly because we're having to do this weird pattern matching like 3 times over, right? With state and then drawing and all of that. It'd be nice if all of our error handling code didn't like pollute this method as much. So let me show you a way that we can actually refactor this. Oh, that's a great question from Rich. So Rich asked, what does the @ operator do? That is the list append operator. So if you have a list on the left and another list on the right, you can append both of them by using the @ sign. Great question. So we can refactor a lot of the error handling logic to make it look like this, where we can say, let new state equals, and then in this maybe block, deconstruct the state into cards in a deck, draw from the deck, and then return back the cards in the deck into these 3 lines of code instead of like this 8-line gargantuan multiple pattern matching thing, which pretty nifty, right? Because it's handling all the error handling logic for us, but we're not having to parse through a lot of match with. Pretty good. So, but you're probably asking, where did maybe come from? Because I don't recall seeing that ever defined. What's up with the let bang, the let exclamation point? Where's that coming from? And where did this return thing come from? Right, a lot of questions. So what we've done here is we've created this new type. In F#, it's known as a computational expression. In other languages, it's called something different. But the idea is that we can create a new type, in this case, a computational expression, that does a lot of this short circuiting for us. And the 2 things you really care about is the bind and the return. What bind says is, if you give me a value and a function, I'm going to match on the value. If the value is none, I'm just going to immediately short circuit, not going to do anything. Otherwise, it has a value called a, and if I have a value, I'll call the function. That's pretty much what bind's doing, and that's what gives us the let bang. That's what actually makes that work. And then the return is actually a return. What this does is, if you give me some regular value, I will wrap it in a sum type. And by saying maybe equals maybe builder, that's what gives us that nice that purple maybe block. That's what actually lets that happen. So let bang is the bind, and the return is the return method, and this will short circuit if any of those things fail. So if we fail to deconstruct the state, it'll immediately return back a none. If we try to draw a card from the deck and we can't, it'll immediately return back none. Otherwise, it succeeded, wraps it all up in a beautiful sum value, and that's what we can consume. If you've kept up to the point of the maybe builder, you've done great. The maybe builder is one that's going to take a little bit of time to process. But the idea here, really the concept I want you to stick with, is that we have a way of how to model when something goes wrong in an application. Maybe because there's an absence of value, or because it's at least with the maybe. And there's other types to handle other things like, well, it's not that I'm missing a value, it's because an exception happened. There's types to handle those type of workflows, but that's a little bit outside the scope of this presentation. So we've covered a ton of stuff, right? And it's a lot to process, a lot to consume. I completely agree. But here's so we talked about Blackjack, we defined the domain, we implemented the domain, and we even implement some common workflows. There's a lot of stuff. But if you're looking for what I want you to take away with, right? You learned about some functional domain modeling concepts, right? This idea of defining types that prevent developers from making a mistake, whether by using a sum type to specify a value, a type can be one of a finite possible set of values, using the product type or records to say that a type can be the composition or the product of multiple other types, right? You've seen concepts of where we said, well, these two things are similar, but they need to be handled differently, like hand and deck. You've looked at stuff about, hey, I've got like this hand, I want to figure out the score, right? And so we talked about how do we break that down and do these workflows and these pipelines. There's a lot of good functional concepts here that we've kind of talked over tonight. And it's a lot to take in, but hopefully a lot of these lessons are kind of clicking a little bit, and at least making you maybe rethink the way you've approached stuff. But here's the thing though, I cannot make you an expert in this in an hour. If I could do that, then I'm in the wrong industry. I need to be like going write books and videos and all sorts of stuff. But here's what I can do. I can give you some resources that helped me improve this stuff. So the first resource I'd recommend is a series of blog posts by Scott Voloshin called Thinking Functionally. Even if you're not a C# developer, and definitely if you're not an F# developer, you should go take a read through these blog post series, because what it'll force you to think about is, how do we write software? How do we actually think about functional programming in a manner? If you're more of an architecture, right, like how do you actually build stuff? Then Mark Seaman, who is well known for his, literally wrote the book on inversion of control and dependency injection for .NET, literally wrote the books on it. He's got a great series of blog posts talking about ports and adapters and functional architecture and how you actually build up bigger applications. His algebraic data types aren't numbers on steroids. You saw some algebraic data types tonight. That's actually what a sum type and a prog type is. They're under the hood, they're really algebraic data types. If you're more of a book person and you want to know like domain-driven design, the book by Scott Voloshin on domain modeling made functional is fantastic. Highly, highly recommend reading it. On that note, I just want to say thanks y'all for letting me speak tonight. Sorry for the technical hiccup earlier, but I appreciate y'all sticking with me. If you've got any questions, feel free to email them to me at cameron@softwarementor.com. I'm also going to be hanging out here for a little bit to answer questions live. As mentioned before, if you missed the slide deck or anything earlier, you can grab the URL here, and I'll also make sure to get these links to the organizers. But otherwise, thank you all so very much.
Thank you.
All right, one of the questions is which book to start with from the references list. I would highly recommend starting with Thinking Functionally, that series, and it's just a series of blog posts. That's the one I'd probably start with, because it really gets you into the idea of like, how do we think about like stuff, like how do you think about breaking down problems, all of it. And that Thinking Functionally series, like in my honest opinion, probably is what gave him the idea, or at least kickstarted a lot of his domain modeling made functional book, because there's a lot of really good concepts there. And I found that to be so helpful for me when I got started. Okay, so Rich asked, I don't understand the way that the deck was randomized. I'm not an expert in F#, so I don't know. Give me a couple of seconds and let me write some code on that real quick. I can give you
sort of function that was plugged into the thing.
Yeah, give me. I know exactly what code snippet you're talking about. If I can annoy a few people, I'm just going to live code something to kind of demonstrate that a little bit. Let me minimize some windows here and start up trusty old link pad here. Man, live coding on the fly, terrifying. So the question was essentially like in the randomizer function, like how did it do stuff? So I'm going to pull over a link pad here and probably bore some people to death, but that's all right. So I'm going to let some numbers be, oh, okay, that's cool. Oh, not log 10. That'd be crazy. So we've got a list of numbers from 1 to 10. So that's going to represent our deck. Fair? I'm going to let random equal new system dot random, I think. Nope, I think it's just system dot random. There we go. And then I'm going to let sorter function be some function. Actually, don't care what it takes. And it's just going to literally call random dot next. And then I'm going to say, oh, I'm going to rename this to numbers. List dot sort by. Let's see what that gives us right there. Oh, because I did not, let me dump that to the screen real quick. So we'll see what that looks like. So in this case, the sorter function says, I don't care what you passed in. I'm just going to generate literally a random integer. And then when it calls sort by on each element in numbers, it's just going to get some random integer and then sort that based on like, and if the F# code's too much, I can port this over to C# if that would help. All right, cool. Challenge accepted. All right, so let's do a C# program here. All right, so same concept as before. I'm going to do some numbers and go and make that list, just say. So I'm going to say var random equals new system dot random. And then I want to have a function that says, if you give me some integer, I'm going to return you back a new integer. Now, in the case of this first integer, pretend it was a card because I don't have access to the card type here because stuff. Call it sorter. Says, I don't care what you give me. I'm going to call random dot next. And then it'll be numbers dot sort. Where's the order by here? And then we'll do sorter, and then I'll dump that to the screen. See if I made any mistakes there. Yeah. Does that help any, Rich? Or no, not at all? Yeah. And it's and so this code is almost equivalent to what F# would have generated. I think the only tweak is, right, like I didn't have to define that type, it just inferred it, but otherwise you got it. Cool. What other questions are there? All right, then, if there's no more questions either out loud or in the chat, I'm going to go ahead and stop sharing my screen. Thanks y'all once again, I appreciated it.
Yes, thank you, Cameron. That was wonderful. So the link for the SurveyMonkey has been posted in the chat. I will also email that out to all the attendees. That survey will be left open for 24 hours and then it will automatically close. So make sure you fill it out in the next 24 hours.
Wonderful. Stephen, if I dump some links into the chat, would that be sufficient or do I need to just email those? What would be the best way of distributing that?
Yeah, go ahead and dump those in the chat and I'll grab them and make sure they get on the meetup.
Perfect. So this should, I'll go ahead and just dump it into the chat, go to meeting, send to, there you go. That will take you directly to the slide deck, articles, and actually all the source code you saw. So if you actually wanted to pull down the code, run it, and play a game of Blackjack, you can.
Okay, wonderful. All right, well, if there's no more questions, we'll give everyone their evening back. Thank you very much, Cameron. That was lovely.
Thanks, y'all. I definitely appreciate it. Till next time.